computing infrastructure. And there is this intriguing idea coming from Ken Church and James Hamilton and Albert Greenberg, where basically we put data into containers and we move essentially petabytes by the containers across the continent. And this is just one slide on a little experiment we have been doing using very low power motherboards that were originally built for home TV boxes. So we built a 36-node cluster that runs off of 1200 watts using Intel processors, and it has a blazing I/O performance, 18 gigabytes per second, because we use a combination of solid-state disks. And these motherboards also had built-in GPUs, so we were able to run a multidimensional regression algorithm for the random forest. And we were able to run in 5 minutes 6.4 billion of these multidimensional regressions for an astronomy problem. So summary, the science community is starving for storage and I/O, and we need to perform the data-intensive computations as close to the data as possible. We need real multi-petabyte solutions now, and since our budget is what it is, we have to build it pretty much ourselves. Current architectures cannot scale very much further, and we need to get off the power wall. Luckily, there are a couple of disruptive changes around the corner, so the multi-cores and the GPUs and the solid-state disks. So we need an objective metric for the data-intensive computing systems, and the Amdahl number appears to be a very good match to these applications. And our future will be in, I strongly believe that our future will be in low-power, fault-tolerant architectures, which will have hundreds of thousands of processors. And so I think they will be similar to these Amdahl data clouds or Amdahl blades, but on a much, much larger scale. And basically the organizing theme of this whole talk was that what we see is that there's a new and forced paradigm of science emerging, where there are many common patterns across all scientific disciplines. So thank you very much, and I apologize again for my cough. Unfortunately, I can't help it. Thank you very much.
So I'd like to thank Alex for his inspiring talk, and I hope his voice survives to allow him to continue his workshop at Snowbird. But now we can entertain questions. I'm not quite certain the technology of getting the questions to Alex, but Alex, can you hear me?
Yeah, absolutely.
So I had a question about the relationship of CyberBricks to ContainerNet. I mean, naively, they seem from just the words, they had the same sort of idea of having a portable data analysis system that you could put around the world or something. Is that somehow the idea?
Well, so essentially you could drive a container to a certain place, then plug in overnight, and then fill it up with data. And then you can essentially then drive the container across the continent in 2 days. And I think they calculated that if you had like 5 trucks going back and forth between the east and west coast, this would be roughly the same as all the networks combined today.
And how might would these containers be similar part to your CyberBrick, or would they have more capability?
Well, so typically it could be anything. So, but one can also think about them like they could only be, for example, just a big container of disks. And one can imagine that, for example, okay, so for a university, these containers would be probably too large, but one can think for the academic environment something like pods. So the mini containers, essentially, an 8-foot by 8-foot cube, something like this. And then you can imagine that you can then every week you can drive such a thing to a national laboratory to Oak Ridge, or if you have a huge petabyte simulation, you run it at Oak Ridge, and then you basically send one of those pods to the final destination, and all the data comes through that.
Oh, I see. So,
and of course, there is the subtlety, so then you would still need kind of quite a lot of InfiniBand ports or fast Ethernet ports, so 10 gig Ethernet ports, so probably 60 ports or so to kind of get the data out overnight.
So instead of having gas stations, we have data stations across the country, and drive our data-heavy brick container to that. So,
and I think they also mentioned the idea of an hub and spoke model, so that you only have to drive your container to essentially to the nearest hub, and then some of the data can be exchanged there. So it doesn't have to be.
Penn State has a question.
Right, Penn State.
So I had trying to follow along with this one thing where you want to connect, like say it's called the hard drive on airplane problem, right? So you were comparing a 10 gigabit Ethernet to these. What's the speed when you go and plug in a hard drive? Like how fast can you then take that data and put it onto the computer where you want to run your analysis, really? Like if you were going to do it with one of these big sets of hard drives too.
Okay, so then one can think of a couple of possibilities. So one is that, so right now we are entertaining ideas that, for example, every hard drive would have a barcode, and you bring it to, and also a little file in the root directory, and then you can bring over a hard drive in a trunk, and but each of them would have to be tray mounted. So they are already in a tray. We can just, then an undergraduate can basically plug those in. And then if we have, say, 10 servers, each with a double 10 gig connection, so this means that would be quite a decent bandwidth to the rest of the system if we can split up this 100 drives among those 10 servers. So each of them would have 10 dedicated trays, say, for the data swap. And this could be plugged in and out probably in a matter of an hour, maybe a little more, okay? But I think 1 disk a minute is not an unreasonable rate if they are already mounted in the trays.
So so following up these questions, there seem to be two types of models: the sort of centralized model where we have maybe these mobile data things to bring the data to the central place, or we have more permanently a distributed solution where the data stays distributed around the world or around the country, and then we try to integrate those systems together. But maybe as in your cyberbrick, having computing next to the data. How do you see those two approaches getting traded off in the future? Is one going to be dominant, do you think? Did you hear my question?
And so people will probably try to aggregate as much data as they can into the big data centers, but certainly there will be no single big data center for science. I expect that there will be probably some national aggregations, and also for a healthy system we will probably have to have a multi-tiered hierarchy even within the US for the scientific data-centric computational centers, whatever we want to call them. Then when the analysis is done, then if we can do all the analysis within one of these data centers, that's perfect. So that's easy. But more often than not, probably we will encounter a scenario that we will still need yet another data set for the analysis that is residing at another location. And then we can do two things. Either we try to move this data set over to where the rest of the data is so that we can do the analysis and all the joins in a coherent fashion, or then we basically do the rest of the analysis, if we can, on the site where already most of the data is, and then move only the temporary result that needs to be then joined with the last bit of the data, bit by bit, over a fast network. And of course, this requires a heavy investment also in the network bandwidth, which so the scientific networks will have to probably go up to 40 and 100 gigabits and so on, connecting at least the major data centers. And then we have to worry about basically this tree hierarchy of the data flow. And essentially, the bigger a data center is, of course, then the bigger bandwidth it will also require. Otherwise, if there is a big data center with a poor bandwidth, then that will hold up all the computations. So it has to be kind of network balanced.
So if we believe that clouds are these clouds are likely to be important here, so you're saying that the model of the future is presumably an analysis cloud connected to a large data center, large MDAL number rich data subsystem, and we'll have a few of those nationwide. Is that right?
Yeah, and I would say that probably, we need a cloud of clouds. So a distributed network of clouds, basically.
I mean, for this to work, we need to make certain that when we have this cloud of clouds, that there is some reduction of data sizes. So as we do the analysis in the individual clouds, then they're going to communicate, but presumably they're going to have to communicate some substantially less data than they actually processed. Otherwise, you would get back to your network problem.
Yeah, that is correct. So this will probably mean also some very some clever caching algorithms. If we already computed some that may be useful for other computations and move that data set already across the better storage.
Now, particle physics has done this sort of with their tier 1, 2, and 3 centers. Is that right, to some extent?
That's correct. Yeah. But there, I think a lot of the data flow is kind of drizzling downwards. So I think there is relatively little transfer laterally across kind of the nodes on the same level of the multi-tier hierarchy.
So as far as I can see, TerraGrid at the moment at least does not support this, and nor does Amazon. So we obviously appear to need substantial new actual architectural work to design this, and also some new investments to actually build such systems. Is that correct?
Yeah, I think so. And in a way, I think the UK has done this little bit better than the US, in the sense that due to the e-science program, they build essentially a hierarchy of these e-science centers with also computational facilities, while also still having a national center. And they try to, so they have regional centers and local centers and the national center. And so this is something that I think it would be worthwhile to think about, that how could one kind of start building out such a hierarchy in the US. So to essentially spend a fraction of the money on high-end computing, basically on data-intensive architectures and also in the middle tier, not necessarily just to build a system that would be in the top 100 computer. Or maybe one way around it would be to also create a new category, a new Gordon Bell Prize, maybe a Jim Gray Prize for data-intensive architectures, and then I think people who want to get on the top 100 list would be more willing and to invest in those machines as well. just to create a psychological motivation